Well, this is logarithmic functions, section 4.2. And the first thing we'll go over is the definition of log. We have our log form. Which looks like this. Log, and then there's a little b here that's smaller and set down. That is a number, and that's your base. And then you got something after that, whatever that is, and then you got something on the other side. Now, if we have it in log form, we can rewrite it in exponential form. Take your base to power the other side equals what follows your log. So b to the p is equal to q. Now, log form, log functions in general, they model certain things in nature. In chemistry, they have something to do with the pH levels, I believe. I never have taken chemistry, but I've had people tell me that. They're also used in the Richter scale. They do mappings, for one thing. They'll map very large numbers or very small numbers into other numbers. Okay, so let's take a look at this problem. 5 equals log base 3 of x. And it says write each equation in its equivalent exponential form. Well, it's obviously in log form because it's got a log. Our number that follows a log is our b, so the 3 will be our b. And then whatever follows that is your q, so the x here is going to be our q. And then the other side of the equals is always your p. Now, exponential form is b to the p is equal to q. So we plug in what we identified. So b is 5, p is 3, and q is x. And that'll be our answer. You don't need to simplify it. They're trying to get you to see the connection between that and exponential form. From exponential form, that's something you can easily graph without using tables or anything like that. Now this problem says write each equation in its equivalent logarithmic form. This is in our exponential form because we got a power here. Now from our exponential form, the power is our p. What's immediately to the left of it is our b. And the other side of the equals is our q. b to the p is equal to q. Once we identify those three items, we are ready to write it into log form. We said our b is 5, so we've got log base 5. Q is 125, so log base 5 of 125 is equal to p, which we said was 3. And that'd be our answer. Drink here. Okay, number 3. Got the fourth root of 16 equals 2. Now this is not in either log form or exponential form, but we can rewrite a radical with a fractional power. This becomes 16 to the 1/4 power. If I were to put a power in a 16, this would be 16 to the first. And whatever power is here is what goes up on top. Whatever your index is, that number in the slot, is what goes down below. And now it is an exponential form. Our form was b to the p is equal q, so our power is our p. What's immediately to the left of it is our b. The other side is q. And that comes from this exponential form right here. So our log form says log base b of q is equal to p. So we plug in everything we identified. B is 16, q is 2, and p is 1/4. And that's our answer. Any questions on the definition of log and the exponential form? Let's take a look at this problem. I'm going to work it, and then I'm going to write down the property that goes with it. It's a very, very simple idea. The property will make it look complex. Now, sometimes it's not so simple to get it in the correct form to apply the property. The instructions here are to evaluate each expression without using the calculator. Now, our base is 5. What we try to do is we try to rewrite whatever's right here as a base to a power. For example, the 25 can be rewritten as 5 squared. If you're able to get the base and the number that's following it the same with a log in front like that, then the log and those numbers are going to cancel. The exponent will drop down, and that's our answer. Property says if you got log base b of b to the p, that's going to equal to p. So if those numbers match, you can cancel log and the b's, and the exponent drops down, and that's our answer. Like I said, very simple idea, but sometimes not so simple to get in that form. We've got log base 2 of 1/8. Now our base is 2, so we're going to try to rewrite this as 2 to a power. And to start with, I can rewrite the 8 as 2 to the third. But property does not allow me to have the 2 to the power trapped in the denominator. Well, we got something from intermediate algebra says you can take that and move it up on top, or algebra 2, whatever you took. When you move anything opposite where it's at in a fraction, the sign of the exponent changes. So 2 to the positive 3 becomes 2 to the negative 3. And now notice that these 2's match. The log and the 2 is going to cancel. Negative 3 will drop out of the exponent, and that's our answer. Number 6, log base 4 of the square root of 4. Nowhere in this chapter do you want square roots at all. We don't have any property that deals with square roots, so you always want to rewrite it before you do anything. Square root is the 1/2 power, so this will be 4 to the 1/2. And actually, after I've rewritten it, the 4's match, so log and the 4 is going to cancel. And the 1/2 drops out of the exponent, and that's our answer. Let's see, log base 9 of 3. Now our base is 9, so we need to rewrite the 3 as 9 to a power. Well, it's not too easy to see, but let's think about some connections here. 3 squared would give us 9, which is the first power, which might work except for we don't have a squared on here. We just have 3 to the first power. Another connection between these is that square root of 9 is equal to 3. Specifically, it's equal to 3 to the first power, which matches the 3 to the first power here. So I could rewrite this as log base 9 of square root of 9. And now that I got this in terms of 9 in some manner, I want to rewrite it out of radical form. So square root is 9 to the 1/2. Nines match, so log and 9 is going to cancel. 1/2 is going to drop out of the exponent, and that's our answer. Questions so far, guys? Let's see, log base 8 of 1. Now our base is 8, which means we have to rewrite the 1 as 8 to a power. Well, anything to the 0 power is 1. So 8 to the 0 would equal 1. So now our 8's would match. So log and 8 is going to cancel. And 0 drops out of the exponent. And that's our answer. I'm going to work this one, then I'll write the property down. It's a very simple idea. Property make it look complex. If you have something of this form, log is in the exponent. and these 3's match, or whatever numbers those are, then just like the other form where those would cancel away, these numbers and the log are going to cancel away, and the 17 will drop out of the exponent, and that's our answer. The property says b to the power of log base b of q is going to equal to q, if you're in the properties. Now these next problems explore graphically. We saw the connection between log form and exponential form, but this shows graphically how do you come up with it. Now on your calculator you have a log button and you have an ln button. They're over on the left hand side and the bottom left. You don't have a base 9. So in order to graph these, we'd have to use something called change of base. Now our ultimate goal is we want to match the function to the graph. First one we're going to look at is f of x. Log base 9 of x. You could definitely rewrite this in exponential form and get the graph that way, because we can graph that easily. If we want to use technology, we can use change of base. Change of base says I can rewrite this as log x over log 9. Change of base says you take your base, whatever it is, and goes on the bottom. Whatever follows your log goes up on top. The benefit of that is we have a log button on our TA3, TA4. We don't have a base 9 button. The newer TA4s do have a capability of putting any base in there, but not most of them. Change of base actually says you can use any base. So I could have rewrote this as natural log of x over natural log of 9. Those are the only two that make sense because there's only buttons you have on your calculator. So you press your y equals, clear, push your log button, push your x key, closing parentheses, divided by, log button, and then 9, and then graph. Now after you graph that, then you should get a graph that looks like this. Now on a TS3, TS4, it looks like it just stops. And they don't just stop. It keeps going forever. It just got so close to the y-axis that it become one with it. Forget that, okay? Okay. Now that's our basic graph, basic function. All the rest of these have numbers associated with them. We're going to talk about what those mean. When we said when the number's inside with the x, it shifts left to right opposite what you think. The -1 would be left to right, and then the -1, -1 make think left 1, so it's really right 1. Now here's our basic graph. If I shift that right 1, that is not going to match this graph. So it's not g of x. Now these negatives that's in front of the log, that's j of x and k of x. When you got a negative in front of the log, that flips it, reflects it across the x-axis. If I look at my basic graph here, that does not look like it's been flipped or reflected across the x-axis. That's what it looked like to be reflected or flipped across the x-axis. And that definitely doesn't look like that. So it's not j of x, it's not k of x. Now a negative inside with the x. This reflects it across the y-axis. And get rid of that. This is passing through 1. If I flip it over here, I don't know if I can do this or not. Let's graph it right. Let's try that again. There. And you can see that flipping it across there, if I put the divided by log 9, you see that it'd be perfect. So to match this graph, because that passes through -1, this passes through -1. So the graph it matches is h of x. Now you could use change of base on each one of these and just graph them and see which one it matches. It's not that hard. Again, what we're trying to demonstrate here is that the shifts and transformations we saw in previous material still apply when we come up with a new function. Now this one wants us to describe the transformation graph of a function. Again, a number inside the x shifts left or right. That's a -3, so shifting right 3. This one would require a change of base. Only if it has a log or ln with no number there is the times when you don't need to use change of base. Otherwise you do. So this one, I'm going to rewrite as log x minus 3 over log 4. Again, whatever your base is, goes in the bottom. Whatever follows your log is what goes up on top. To graph this, you press your y equals, clear, push your log button, x key minus 3, closing parentheses, divided by log button 4, and graph. and that'd be your answer. Now, if I look at I took the exponential form and I swapped my x's and y's. This is our exponential form, and this is log form, and they're inverses of each other. So if I were to start with one of these, like this one here, and swap out my x's and y's and solve for y, then I get the other one, or vice versa. So you remember exponential grew slowly, and then flew out of sight. Well, these will climb rapidly, and then level off. So you see these. Probably medicine is the biggest place where you'll see like things like this, because some medicines they give you will like really combat viruses in your body, bacteria, whatever it is that they do. I'm not a medical person. And you'll feel really good at first, and then it levels off, and then people don't feel as good. Well, that's because it's leveled off. You don't feel that dramatic increase. Now these next ones, or at least this one, there is no number here. Now, if you don't have a number, special basis, you just have log. Well, by default, this one has a base of 10. This is referred to as the common log. If you have ln x, your base is e. Now, e is that number like pi, keeps going forever, 2.7, bunch of decimal places. And this is referred to as a natural log. We've been working log for approximately 30 minutes so far. I probably made 50 mistakes. Those of you that have been kind, or those of you who know what mistakes are, have been kind, haven't said anything. I'm happy with those mistakes. I'll keep on making those mistakes. That's a lot of screw ups in 30 minutes time, though. Those of you who are going on mathematics, log is never uppercase. It's always lowercase. Like this. You never have natural log of x like that. It's lowercase. I deliberately write it wrong because I used to cover logs. It'd be a 3-hour class I cover logs in. I'd say log this, log. We use the definition of log, log x, natural log of x. I said that maybe 500 times in 3 hours time. Because you just say log over and over. Never failed. I'd have somebody come up at the end of class and they'd ask me what this 10G was. I kept writing on the board. You didn't make the connection. 500 times I said log with writing down 10G. So I knew eventually I would snap if I kept getting that question seriously. So I deliberately write it wrong. I don't want to get that question seriously asking what it is. Of course, this you can figure out what what they're to ask, what that 1n is. I keep writing on the board. I still get this whenever I teach online, because people will see this and they'll think it's 10G, 10G. Kind of makes sense when you got 5G and 4G and so forth. I can see it. If you put 10G in on, when you're taking the test, it'll count it wrong. It's looking for an L and an O, so keep that in mind. I don't know if it'll count it wrong if you put the uppercase, but it's supposed to be lowercase. There's my disclaimer. I'm still going to do it wrong just because I avoid the 10G issue. I'm sorry, there was a famous popular thing to use in computers. If I can remember it. Something like this. Once in computers, when you go out there and like somebody can't get their computer to come on, they got it unplugged, something like that, and you come back and, well, that was an ID 10T problem. So reminds me of that log issue. Yeah, people in computers aren't necessarily that nice. They'll make fun of you if you ask them something really stupid, or you go back. Now I've done things like that myself. But okay, now this one we want to this transformation is easy. +3 at the end is up 3, but the graph is the important part. Now I want to graph this. Now I got a log button, so I don't need to use the change of base. So I'm going to press my y equals, clear, push my log button. When you push the log button, it puts the beginning parentheses on there for you. And so then you put your X key in. And since it put the beginning parentheses on there for me, I have to do a closing parentheses before I do the rest. Or if you go on the newer calculators where it's like math print mode, you do a right arrow key to get out of the log. And then +3. And then graph. So again, no change of base because there's no base there. It's just log, which is base 10. So log x +3. And as you can see, the +3, it's been shifted up 3 units. Now, it still looks the same as the other ones. You'll find that these graphs don't change a whole lot. I mean, negatives and numbers will shift them up and down, left or right, flip them across the x-axis, flip them across the y-axis, but they'll still have the same shape. Just as the exponential graphs all have the same. Let's take a look at this one. Got f of x equal natural log of 1/3 x. Okay, I want to graph it. Again, we don't have to use change of base because we have an ln button. So you push your y equals, push your ln, then you do 1 divided by 3 x key. and then graph. You don't need to actually close parentheses at the end unless you want to. This would be our graph here. Now, I'm not very good with fractions and what it does in terms of shrinking and stretching. But you see down here, when you put the 1/3, then that moves it closer into the x-axis. So I guess that would be shrinking it toward the x-axis. Or if you think about your y-axis, you could think that is looks like let's see, the red is this one, so that's stretching it away from the y-axis. It all depends on how you want to view it. Now these next problems talk about domain. Note, you cannot have log of 0 or log of a negative number. So, domain of a log function. Set what follows the log greater than 0 and then solve. Greater than 0 because it can't be negative and can't be 0. So in this problem, we have f of x is equal to log base 3 of x minus 5. The instructions are to find the domain. So our steps say to take what follows your log, the x minus 5, and set it greater than 0, and then solve. So I take negative 5 over, and our domain is x is greater than 5. Written in interval notation, that'd be 5 comma positive infinity. Now this next one's an oddball case. F of x is equal to natural log x plus 3 squared. And same instructions, want to find domain. Well, it doesn't change. You still take what follows your log and set it greater than 0. But let's think about what happens when I square something. If I got a negative 2 squared, that gives me a positive 4. If I got a 2 squared, that gives us a positive 4. So it appears like when we square anything, it's always positive. So when you're asking when is it greater than 0, it appears like it's always greater than 0. Now there is one issue, and that's there's a value we can plug in here that causes it to equal 0, which would not be greater than 0. So how I can find that is if you just set the x plus 3 equals 0, you get x equals negative 3. If I put negative 3 in here, negative 3 plus 3 is 0. 0 squared is 0. 0 is not greater than 0. So x cannot equal to negative 3. It can be equal to anything else, but can't be that value. Now you could go through those same 2 steps I just gave you, but when you set it greater than 0 and you solved it, this would be a polynomial inequality. You go through polynomial inequality steps, it would still be an oddball case over there. So either way, it's kind of different. Here we got log 1 and 4 zeros. And it says evaluate and simplify each expression without using the calculator. These are back to the problems where you can use that properties I gave you. I gave you 2. First off, though, we have to note what our base is. When we just have log, that's base 10. So the question becomes, can we rewrite this as 10 to the power? And this would be 10 to the 4th power. If you remember this from way back when you first covered probably the metric system, the number of zeros dictates what your power is going to be. And now the 10s match. So our property says the log and those 10s are going to cancel. 4 will drop out of the exponent. And that's our answer. Number 17. Got a natural log of 1 over e to the 3rd power. Now, one thing to note is that natural log is base e, so I can put it there just to emphasize it. Technically, it's incorrect to put the e there, but we will. Now, I want to rewrite this as e to a power, and that's easy, because we saw earlier that from property in intermediate algebra, algebra 2, you can move something opposite where it's at in a fraction. So I move the e to the positive 3 up on top, and it becomes e to the negative 3. Now, all of our properties that we have for logs apply no matter what your base is. So the fact that this is base e does not change anything. Still works. Since these e's match, the natural log and the z's cancel. Negative 3 drops out of the exponent. And that's our answer. Number 18. E to the natural log of 9x. Now remember, natural log means base e, so I'll put that there to really emphasize it. And we saw this property back, first part of this section. If these numbers match, remember e's are just numbers. If those numbers match and we have a log, those numbers and the log will cancel. And what follows that will drop out of the exponent. And that's our answer. Number 19. 10 to the power of log 5x minus 2. Same instructions. We want to evaluate this without a calculator. The fact that we have log here and there's no base means by default it's 10 if it says log. Just like the previous problem, if these numbers match, log and those numbers are going to cancel. 5x minus 2 will drop out of the exponent. And that's our answer. Log is short for logarithm. This is natural log. If you're wondering why it isn't an NL, natural log, it comes from the French. French came up with this. Log natural is what that stands for. So that's why it's LN. Logs you use all the time, possibly millions of times a day. When you're getting watching TV, for example, watch 2 or 3 hours of TV. The signal is coming through, and they transform the signal so it's a smaller in a smaller form via logs. That's one of the algebraic techniques they use. So your little box sitting there is using logs to put it back into the proper form. If you watch videos on your phone, same idea. So you probably won't do anything with logs, but you use it throughout your entire life on a daily basis, sometimes millions of times. There's a lot going through in a signal. You talk about an hour program. Now, I don't know how many I say that, but maybe I'm making it up. How many is in a television show? It's in a HD. Okay. High definition TV. It's interesting. I think isn't a video game 60 frames per second? Yeah, I would have thought TV would have more quality, but it has less. Huh. Or yeah, higher. Let me see if I can. 3D Space Invaders. This we'll talk more about. I'll show this video again once we get to matrices. Now, if you look in the upper left-hand corner, try to shut the sound off. Let's see there. Okay. You see in the upper left-hand corner, that's how many frames per second it's going through and changing in this game. So that gives you an idea. You're talking about a signal coming in your movie. It's doing a lot of transformation. Questions on any of that? I'm gonna go ahead and give you the formulas for the next section. Um, Although I think we'll probably hold off working problems. So I'm kind of slowing you guys down a little bit and I'm speeding up the other class. It's been driving me crazy. You guys are out of sync. So I'm pushing them hard and I'm kind of slowing down on you guys, at least until you guys are both together. Should have done that at the very beginning. I'll type these up there next time also, just for anybody that's gone. We got three main properties of logs. If you have log of m plus log of n, you can rewrite that as log mn. So addition becomes multiplication. Or if you have as multiplication, multiplication becomes addition. Log m minus log n is equal to log m divided by n. Subtraction becomes division, or going the other direction, division becomes subtraction. If I had p log m, I can rewrite that as log m to the p power. What that entails is if you have a number in front of your log, although I have seen some books use a variable there also, but if you have a number in front of your log, you can take that number and put it as your power. First one's called the product rule, next one's the quotient rule, and this is the power rule. Now, way back when, and there's more to it than what I'm showing here, but if I asked you to go ahead and multiply these numbers together, so if I asked you to multiply those numbers together, you could do it, right? But that'd be a horrible, horrible problem. You probably never multiplied numbers by hand, I should say. You never multiplied numbers that huge before by hand, have you? I don't think anybody was so mean they ever made you do a problem like that. Well, back in ancient times when they didn't have nice T83, T84s, no electronics at all, and if they had to multiply these two together, that would have been a nightmare. So somehow, and I never have cared enough to learn the technique, I just remember them telling me this in the history and math course, they would use logs, and they'd rewrite that using addition. Now, there's more to it than that because you have to look it up in tables and so forth. But if I were to ask you to add these two together, could you add it by hand? Yeah, pretty easy, right? And you'll see that if you go on to take that principle, if you go on to take calculus of some sort, this calculus can take something that's very nasty and eliminate different operations and take it down to something real simple. Whenever I've taught Calc 1 in the past, especially on the main campus, I have students show them how to do something. We do it the hard way first. And one student went over and talked to the tutors, and the tutor said, "Why are you doing it the hard way? Why don't you use logs? Logs allows you to split them apart into easier pieces you can work." And The student came back and asked me that. I said, well, the idea in calculus is you learn the hard way first, and then you do the logs. So logs is a vital tool when you're taking Calc 1, if anybody has to go and take that. I know a lot of your degree, well, some of you may not even know where you're going yet, what you want to do. But if you do end up with in a field that where you take Calc 1, then you'll appreciate logs in. Well, we're going to go ahead and stop there. I'll be here to the end if you have questions. But the only section you need to worry about is 4.2, and we'll go into 4.3, working problems next time.